So in atomic structure, first we should know about different models. So the primary models are Dalton atomic theory. That is the most basic one. After that, that Thomson model, which is also known as plum pudding model or watermelon model, and thereafter Rutherford model, which is based on Rutherford Scattering Experiment, and then finally we have to look into Bohr's atomic model. Bohr's model. Now, for Rutherford model, important is Rutherford scattering. So if you look into the Rutherford scattering experiment, you know what it has been done. So Rutherford scattering experiment. So this we will discuss quickly because there are some graph, there are some relations, there are some numerical formulas which are required for problem solving. So in Rutherford scattering experiment, we usually take, so let me draw like this. In Rutherford scattering experiment, we have taken one lead box because we have to keep one radioactive material inside it. So there is a lead box, and here we have taken one radioactive material. Actually, it was taken at that time polonium. So this is the lead box. Why lead box? Why we use lead box to store the polonium?
So because very reactive.
Because lead box will absorb the radioactive radiations, and it will prevent avoiding to the other place. So it will be a thick lead box, and a very small amount of polonium will be there. Now, since polonium is a radioactive element, it will emit alpha particles. These alpha particles are made to strike on a thin gold foil. So why gold foil is taken at that time, or in fact now also we use gold foil. What is the reason that we have taken gold foil?
So I'm not sure about that.
So because there are three important reasons. First, gold is highly malleable, so you can draw very thin sheet out of it, extremely like 8 to 9 atomic layers. You can draw very thin sheet out of it. Second thing is gold is almost neutral to many reactions. And third one is it is comparatively heavy because we need heavy metal, because alpha particles are going to hit at a great speed. So we need the heavy material. Now this gold foil is kept here, and beyond that gold foil, we have one circular screen. This screen is basically made up of zinc sulfide. Now what happens that when alpha particle hit this screen, you will see like all type of some spot, like bright spot will be there. That we get when like just like when you put oil on any paper, you got oil spots. Similar thing you will get here. So zinc sulfide screen was used to collect those spots. And interestingly, it was found that most of these spots are found here only. Most of these spots, about 98% spots are found here. Few spots we found in a scattered place, and very few spots, extremely few spots, like 8 out of, you can say one out of 8,000 approx, we got extremely at the back side of the circular screen. So what are the observations? Observations are most of the alpha particles, it passes through the gold foil. some alpha particles got scattered, and few alpha particle got 180-degree bounce. Okay.
Yes,
And
sir.
based on these three observations, we have concluded this thing that since most of the alpha particles passes through the atom, so most space is empty. Most space is empty. This is one. Then few alpha particles got scattered. That means there must be some positive charge, which we use this term nucleus, because the positive charge will scatter the positively charged alpha particles, and a few alpha particles bounce back by 180 degree. That means this nucleus has a very very high density. That means all the mass, now we can conclude that all the masses of atom is situated at that particular center, which is called nucleus. Now based on this,
Yes.
we have Rutherford model. This you are already aware of. Now we have
Yes,
to
sir.
look into some of the formulas. So yes, please note it down. Then we will see some formula. So we will see. Okay, done. Is it done?
No, sir. One sec.
Okay. So we can easily say that what is Rutherford model. In Rutherford model, it was said that this atom is spherical in shape, and in between we have a small uh, space which is called nucleus, where all the positive charge is concentrated, and outside the nucleus we have electrons which revolve around in circular orbits. Okay, this was the basic proposals of Rutherford model. Okay, is it done?
Yes, sir. Sir, can you once again repeat why lead box was used?
Because you are using one radioactive material, no? Uh, it will emit harmful alpha particles are harmful. So
Yes.
it is emitting harmful particles radiations all around it. So we have to block all the sides, except we will keep one opening through which we will allow the alpha particles to come through and hit the gold foil.
Okay.
Yes. Is it okay? Shall I remove this one?
Yes, sir. Yes. Done.
Okay. Now, what are the formulas that are needed? So there are two formulas. So we will draw first graph. So first thing we will see the number of alpha particles, scattering at an angle. How this term varies. So we have to draw one graph like this, and like one axis, and there is one more axis here. Let us name this axis as n theta, and this axis as theta. So basically theta is the angle of scattering, and n theta is the number of particles which is scattering at the given angle. So it was found the graph is going like this. This is the graph. This is the graph which is going like this. Okay.
Yes.
Now we can see that number of particles which are getting number of particles is scattering at an angle, it is inversely proportional to theta. If theta is more, number of particles which is scattering at that angle will be less. So it means that if we take here 180 degree, there is very less number of particles which got scattered. Whereas if you look into a very small angle, maybe 1 degree, 2 degree, you will see that there are lot many particles which got scattered by 1 degree. Now scattering means this one. If this is the nucleus and the alpha particle is going like this way they scattered. So we mean to say this angle. Here, if we draw this dotted, this is angle theta. This is angle of scattering. So less angle, smaller angle, more number of alpha particles. And we can see that at approx 0 degree, we have large number of particles which pass through. It means that large number of alpha particle goes undeviated at 0 degree scattering angle, whereas very few alpha particles got scattered by or got bounced back by 180 degree. Is it okay?
Yes, sir.
Okay. So now we will see what is the relationship between n theta and theta. So relationship is this. N theta is directly proportional to this equation is quite big, but we will just look into this. 1 over sine 4 theta by 2. I write down this one. And theta directly proportional to 1 over sine 4 theta by 2. Sine to the power theta by 2. We will see one question based on this. Noted?
Yes. Yes.
See, if the question is like this, if 2000 alpha particles in Rutherford experiment, if 2000 particles scattered by 60 degree, then find how many alpha particles scatter by 90 degree. So this is just one example how to use that formula. So question is that n 60 degree is equal to 2000. So what will be n 90 degree? This we have to calculate. So how to do it? We will do like this. Since we know that n theta is inversely proportional to sine 4 theta by 2. So we will write like this: n 90 degree by n 60 degree is equal to sine 4 60 by 2 sine 4 90 by 2. So sine 4 30 degree divided by sine 4 45 degree. It simply means that sine 30 divided by sine 45 to the power 4.
Yes.
So what is sine 30? 1 by 2. What is sine 45? 1 by root 2 to the power 4. So it means that it is coming to be 2 to the 4 1 by 16 divided by 1 by root 2 to the power 4. So 1 by 4. That means 1 over 4. So 1 over 4, that means our answer will be n90 degree is equal to 1 over 4 into 2000. So answer is 500. So 500 alpha particles will scatter by 90 degree.
Okay.
Okay. This is one relation. There is one more relation that we will look into. What is that relation? Okay, first you see this question and this solution. Is it okay? Any doubt here?
No doubt.
Okay. Now, we have another relationship that we can discuss, that is impact parameter.
Okay.
Impact parameter. All these relation has been asked in exams. So impact parameter means if we take this as the gold nucleus, for example, and we have thrown a beam of alpha particles towards it, a beam of alpha particles towards it. So you consider straight line as like a kind of principal line which is passing through this. So any alpha particle which is following this straight line, middle line, is it is going to do the head-on collision with the nucleus, and we will say that for this we have impact parameter 0. And for the other alpha particle, this distance, the perpendicular distance of the motion of alpha particle from the mid line or the central line is called impact parameter. So the farther the distance of alpha particle, impact parameter will be more. Understood, na?
Yes, sir.
Now, how impact parameter affects the scattering angle? So it has been found that impact parameter is directly proportional to 1 over tan theta by 2. This is again another relation. So question may be asked that, okay, there is one alpha particle which is at a distance of, let's say, 1 micrometer from the central line. It is scattering by some angle. Then what is the scattering angle for another alpha particle which is at double the distance from the previous alpha particle? So we have to use this. B is directly proportional to 1 by tan theta by 2. Okay. One thing to see, if impact parameter is less, bouncing will be more, like scattering will be more. As and when it simply shows now that if B increases, theta will decrease. So the alpha particle which is at a very large impact parameter, it will simply go undeviated. It will not scatter at all.
So over here, B
is the perpendicular distance of the line of motion of alpha particles from the central line. Central line means that a line which is, you can take the line where the alpha particle is supposed to do the head-on collision with the nucleus, target nucleus.
Okay.
Got it?
Yes.
Okay. Then one more numerical formula is there, that is distance of closest approach, that we have to see now. So first you write it down, then we will see distance of closest approach. Is it okay? Noted?
Yes. Yeah, done.
Yes. And now we will see the last numerical formula related to Rutherford Scattering Experiment. Although there are many other relations, but that is not required for our point of view. So now we have another one, distance of closest approach. Distance of closest approach. So what happened that we are talking about one alpha particle which is having impact parameter 0. So it is going to hit it will try to hit the nucleus, target nucleus. So let's say target nucleus has atomic number Z. So its charge will be Ze. Whereas alpha particle will have charge of 2 electron, that it is also positive, it is also positive. So obviously the alpha particle which is going to do the head-on collision, it will be unable to strike it, it will be unable to touch it, because at a certain distance it will bounce back. This distance is called distance of closest approach. So distance of closest approach is the minimum distance to which alpha particle can reach towards the nucleus, the target nucleus.
Yes.
Both are positive. So both will be bounced. So alpha particle will be bounced back from a certain distance. That distance is called distance of closest approach.
Okay.
Now, what is happening here? When we launch the alpha particle with kinetic energy k, then at that moment it has potential energy 0. Whereas kinetic energy is half mu square, where u is the speed with which it is launched. Now, at the point of distance of closest approach, its kinetic energy will be 0 because it is just going to bounce back. So it will be momentarily at rest. It will be having kinetic energy 0. Whereas potential energy will be K Q1 Q2 by D. So we have to equate this as per conservation of energy. So we will write half mu square is equal to K means 1 by 4 pi epsilon naught. Q1 is, let's say, the charge on the alpha particle, and Q2 is charge on the nucleus, divide by D. From this, we can calculate what is D. So D will be Z E square by this one pi epsilon naught m u square. This is what distance of closest approach. No need to memorize this last formula. Just you have to understand that how we have calculated.
Yes.
Okay. So these are the three important relations or numerical formulas which we may require in different competitive exams, which is related to Rutherford Scattering Experiment.
Yes.
Now, after this, we will look into the Bohr's model and what are the different relations that is required there, that we will see. Okay. Yeah. Thank you.